Hi, I'm Barnaby. I'm the team lead for StratZ's team testing My Patience. We'll just go over our preliminary design review. This is our team structure with myself as the team lead and Alice as our vice lead. And here's a lovely little team photo with most of us in here. There's 3 people missing. The goals of our project are fairly simple. Goal number 1 is to fly our rocket testing My Patience to as close to 2,500 feet as possible. The second goal is to fly the customer's payload, our rideshare payload, as well as a reference Easy Mini in order to count that as one certification flight. And the final goal is to design the rocket to be modular so we can fly it in multiple different configurations in order to meet our certification requirements with the UKRA. As a brief mission overview, our rideshare payload will be Firefly Ultra. This is part of our wider certification campaign, but the revision 1 will be entirely devoted towards this competition. Firefly Ultra is an all-in-one dual pyro channel and multi-sensor flight computer, and the vehicle will be sending to the NRC. It will be our certification vehicle in a very special NRC configuration. A brief look at our budget. Our overall cost is expected to be about £1,622. Approximately 65% of this money is coming from the University Alumni Fund. To fill the rest of the gap, we're planning to apply for the UKSED's NRC bursary, and we're actively looking for industry sponsorship. To break down a few of the prices, the motor and casing comes to about £91, and the rest of the mechanical costs of the vehicle come to about £300. The electrical costs come to about £900, and travel comes to about £330, accounting for vehicle hire and petrol for 3 days of travel.
This is an overview of the mechanical timeline for NRC. Since StratZ's is also participating in the MAC 25 competition this year, we have taken those deadlines into consideration, as well as our exams specifically for planning our manufacture period. These are the potential conflicting dates. We have a lot of overlap in April and May. Therefore, to try and mitigate this, we have requested a 2-week extension on the MAC 25 flight readiness review. Hopefully this won't affect any of our deadlines for design, manufacture and flight readiness reviews for NRC, but we're working on trying to make sure that there's less conflict there. There's a more legible version of the Gantt chart in Appendix A. So on to the overview of the rocket. We are doing a single deploy rotor eject, and you'll notice that we have specific pins and screws in these sections. These are so that we can have changeable parachute bays. We're planning to using the exact same vehicle for our certification campaign for Firefly. As part of that, we want to have adjustable amounts of space for parachutes because it will be able to dual deploy, hence there's a bit of potential break there. Our aft section is completely replaceable, hence why there's more pins there, but you will only really be seeing most of the 29mm. The 38mm other design isn't necessary for NRC. For the PDR, we created some preliminary CAD. This is just a render of the model as a whole. In the next section, we'll be working from top down, talking about the different sections of our rocket.
So now we'll be covering the fourth section in nose cone. We chose the 1 carbon nose cone shape because it minimises drag. The nose cone will be 3D printed using PLA+. The reason for this is because it's environmentally friendly and it's easy to work with. We have some insertions to the U-bolt down here. These might change in the future, but this is just so we can attach a short cord to the nose cone. It's hollow for now, but we'll add ballast in the future to add stability, and we'll secure the nose cone to the bulkhead using a box it.
Here are some diagrams of our modified payload adapter. As you can see in the diagram here, the base of the payload adapter is slightly widened to match the airframe diameter. However, the interface with the custom payload itself is unchanged. We plan currently to power the payload through the XT30 connector at the bottom of the payload adapter.
This is the battery bay. It fits onto threaded rods, runs directly to the top of the AP bay where it's locked into place with a pin on its base, and there are holes for threaded inserts that lock 2 pieces of the accurate together. It's currently configured for 3 RS Pro 18650 cells, which slide in sideways, and there are devices to aid with their removal.
This is the AV sled. It's held in place by 2 threaded rods and a locking pin to ensure it maintains in the correct orientation. It currently contains 2 slots for certified flight computers and 1 slot for our experimental flight computer. In this configuration, it has a storage for a market spot camera, which may be removed as development continues. From this point onwards, all requirements will be listed in Appendix B.
I will now take you through the aft of the rocket. The aft of the rocket will contain a 29mm motor mount tube made out of phenolic, centred by 3 centering rings. The top 2 being made out of laser cut plywood, and the rearmost being made out of 3D printed plastic contained within the fin can. The fin can will also act as the motor retainer, with a threaded plastic insert screwing into the bottom, similar to off-the-shelf retainers. The body tubes for the parachute bay above will also be made out of phenolic. This is because it's just a simple enough material to work with. The parachute bay will also be extendable, should during our start campaign the rocket be flown higher and heavier and will need larger parachutes. The fin can will also be thoroughly tested to ensure that it is viable and safe.
Before the flight, the flyaway waveguides will be tested with the standard 10-10 router, preferably before the critical design review. They'll also be using a fiberglass rod to act as a hinge rather than the carbon fiber rods we used last year. We're still deciding between the use of torsional springs and linear springs for this application, and in the open rocket model we'll see later on in the slides, these are being simulated as a set of boosters.
So, now we're going to talk about motor selection. We've chosen the Aerotech reloadable G76 Mojave Green motor. It has a higher apogee achieved with the G64, however the G76 has a higher velocity off the rail, which is one of the things we're currently lacking in our simulations. It costs £22 from Wizard Rockets. Here's a link.
So now on to our launch vehicle simulation section. We model the launch vehicle in OpenRocket. One of the features of this is our booster pods, which we've used to model the FARGs, which have been covered in the previous section. We've created simulations for each of the available motors in the NRC competition, and these are listed on the upcoming slides, as well as all of the metrics of the flight. Each of these simulations, however, one of the problems is that they do not meet our minimum required velocity while exiting launch rail. This is specified in requirement ORK 007. We've been informed during the welcome sections to the competition that we're not likely going to meet every metric of flight that we want. And one of the main ones of these is our apogee. We have traded off quite a lot of apogee performance for a lot of extra features in our avionics bay. These include our flight computer, which we're planning to certify with the UKRA, which requires a camera to measure some of the things that it performs during flight in order to validate its functionality. We're looking into apogee gains using things like mass savings or diameter reduction, but these are things that we're going to do for CDR and not PDR. The highest performance motor, I should also add, has been used for all of our simulation plots. So these are the requirements that I've gone over. These will be covered in more detail in the appendix, you should be able to see them well. Here's our open rocket model with all the statistics of each of the motors. Here's our altitude versus time plot. And here's our stability versus time plot.
Moving on to the rideshare payload design. This is the fourth iteration of computers from Stratsad's Firefly Ultra, which we are intending to certify with UCRA, this being the maiden flight of the computer. It's intended to be dual deploy capable with dual redundant pyro safety. And we're fitting so many advanced sensors into a tiny package of just under 30 millimeters by just over 100 millimeters. These advanced sensors include a GNSS receiver that will give us good GPS data over the entire envelope of flight, as well as a barometric and inertial sensors for use with sensor fusion. Moving on, we've got several key requirements for Firefly Ultra, over 100 in total, but these are the ones that align most with the specific NRC requirements. A full list will be included in the appendix. The main ones being that it will be a 6-layer PCB. It will include a barometric altimeter among the other advanced sensors that will record the data and transmit those over the telemetry link. It will also indicate the altitude on boot up of the previous flight, so that when we recover on the ground, we can get the max altitude very quickly. And it will provide all recorded sensor data over a USB interface for plotting on a laptop.
We have our ground station with 2 antennas allowing us to communicate over 2 frequencies, or we can get up to 4 telemetry sources with time division multiplexing. Got a large LCD display screen which allows us to see key telemetry data from the rocket. USB data streaming and power, so that we can power it and interface with a laptop, and an integrated battery to enable it to be mobile for recovery of the rocket. We have some key requirements for our ground station, including it must be able to receive telemetry from Firefly Ultra. It needs to be able to display this on the LCD display, and it needs to be able to provide it over an integrated USB port connection, as stated on the previous slide. We will verify that it meets these requirements through demonstration, testing, and inspection.
For a brief look at our project risks, the big 2 risks we've put at the top of the table are having insufficient funds and not leaving enough time to finish the vehicle. And just to close off, as we move towards the critical design review, our mechanical team will be looking to start manufacturing and testing components, as well as the materials they'll be made of, and also looking at weight-saving measures for the open rocket model. The electrical team will receive their development board in the next few weeks, and they plan to start testing individual components as well as prototype and test for their ground station, and finalise the schematics for Firefly Ultra. Finally, I'd like to thank our sponsors, SolidWorks, RS Group, Altium, JLC PCB, and the University of Strathclyde Alumni Fund. Without any of these, this would not have been possible. Thank you for listening. Looking forward to flying in July.